In recent years, multimodal large language models, MLLMs, have begun to transform human-computer interaction from simple, surface-level exchanges into something far more nuanced, emotionally intelligent communication. Imagine a virtual counselor that doesn't just detect your sadness from a video, but understands why, not just by labeling your emotion, but by explaining it in a way that feels genuine, coherent, and trustworthy. That's the promise of emotionally intelligent AI. But here's the problem. Current MLLMs often fail at this. They may correctly predict an emotion, say, sadness, but their reasoning behind it can be inconsistent, contradictory, or even emotionally disconnected. A model might say, the person is sad because they're frowning, while the video shows them crying with eyes closed, clearly not a frown. That misalignment undermines trust and limits real-world applicability. So how do we fix it? We propose a novel framework called the Emotional Rationale Verifier, or ERV, designed to ensure that the reasoning behind emotion predictions is not only accurate but emotionally coherent, aligned with both the predicted emotion and the actual ground truth. Let's break this down. At its core, the challenge lies in training models to generate explanations that are not just plausible, but faithfully consistent with the emotion they are trying to explain. Most existing approaches rely on supervised fine-tuning or reinforcement learning that optimizes only for final prediction accuracy, ignoring the internal logic of the explanation. This leads to a critical flaw. Models can learn to cheat. They generate explanations that sound human-like but don't actually reflect the emotional content of the input. The system may predict anger correctly, but the explanation could focus on background noise or clothing, completely missing the emotional cues. To solve this, we introduce a two-part innovation. First, a lightweight emotional rationale verifier, and second, a new explanation reward mechanism. The ERV is a distilled version of a large language model, trained specifically to judge whether a given explanation supports the target emotion. But instead of using the full LLM at inference time, which would be too slow and costly, we train a compact, efficient model that mimics the reasoning of a larger one. How do we train it? We start with small, high-quality datasets like EMER and MERR, where human experts have annotated both emotions and explanations. But these datasets are too small and imbalanced to train a robust verifier. So we augment them. Using existing MLLMs like R1 Omni, we generate thousands of emotional descriptions from large-scale datasets like DFEW and MAFW, videos of real people expressing emotions in the wild. Even though these models sometimes get the emotion label wrong, their explanations are often rich and emotionally grounded. We then use GPT-4 to assign up to 2 emotion labels to each generated description, creating a pseudo-labeled dataset of over 20,000 examples. To fix class imbalance, where emotions like disgust, fear, or helplessness are underrepresented, we use few-shot prompting to generate more examples for those rare categories. The result? A highly diverse, balanced dataset that trains ERV to recognize emotionally salient content across a wide range of expressions. Now, during reinforcement learning, instead of just rewarding correct predictions, we now reward emotionally coherent explanations. Here's how the reward works. For each generated explanation, we split it into individual sentences. Then ERV evaluates each sentence independently. If a sentence talks about someone's clothes or the room lighting, neutral, non-emotive content, we filter it out. Only emotionally relevant sentences count. Then, we compute a reward based on how many of those emotionally meaningful sentences align with the ground truth emotion. For example, if the target emotion is fear, and 3 out of 5 emotionally salient sentences mention trembling hands or wide eyes, both strong fear indicators, we assign a high reward. This ensures the model doesn't get rewarded for long, meandering explanations full of irrelevant details. Instead, it learns to produce focused, emotionally grounded reasoning. We integrate this explanation reward into a powerful reinforcement learning framework called Group Relative Policy Optimization, or GRPO. This method compares multiple generated responses at once, allowing the model to learn what makes one explanation better than another, not just in terms of accuracy, but in consistency and coherence. And the results speak for themselves. On benchmark datasets like MAFW and DFEW, our model achieves 48.93% explanation emotion accuracy, a significant jump from the baseline's 32.41%. More importantly, faithful consistency rate, which measures whether the explanation, predicted emotion, and ground truth all agree, improves from 27.27% to 43.57%. Even more telling, in human evaluations, participants rated our explanations as more informative and emotionally grounded, giving them a higher average score, 3.52 versus 3.42, and a 53.6% win rate over the baseline. But what makes this framework truly powerful is its practicality. Unlike other methods that require massive annotated datasets or architectural changes, our approach works with existing models. It doesn't need new training data with paired explanations. It doesn't modify the model's architecture. It simply adds a lightweight verifier and a smarter reward signal. This makes it deployable, scalable, and efficient, ideal for real-world applications in mental health counseling, educational guidance, and empathetic AI assistance. And the implications go beyond emotion recognition. This work introduces a new paradigm, evaluation-driven reasoning. By designing metrics that probe emotional coherence, Like EEA, EPC, and FCR, we can now measure not just what a model predicts, but how well it reasons. We've shown that these metrics are robust across different LLM families. Whether you use GPT-4.1 Mini or Gemini Flash 2.5, the results hold. And in human studies, agreement between participants and the evaluator LLM reached 92.9%, confirming that our framework captures human-like understanding. In conclusion, we've taken a critical step toward truly human-like AI interactions. Our emotional rationale verifier doesn't just improve accuracy, it ensures that the why behind every emotion prediction makes sense. It builds trust. It enhances transparency. It brings us closer to systems that don't just recognize emotions, but understand them. This isn't just about better models. It's about building AI that can truly connect with us, emotionally, logically, and ethically. And that's the future we're working toward.